All right, good afternoon, everyone. My name is Tom Douglas. Welcome to our second installment. I had one last night for Asia, and this one's focused for Europe. Our webinar titled An Introduction to Imaging Phantoms Used in Quality Assurance for Radiology. We're doing a little differently this time. You can probably notice the platform we're trying StreamYard. And what's also new is that this is streaming on LinkedIn. So if you are joining us on LinkedIn, thank you. A little agenda of what we're going to cover for today. Purpose of phantoms. I'll look briefly at some standards and regulations, walk through some typical radiology phantoms, and then we're going to take a look at some of the images and show how things are analyzed. And like always, we'll have spot to take some questions at the end. Tomas, our medical physicist, should be joining us, so he can be helpful for that. I think a lot of you already found the comment section. So if you have questions as we're going or as we get to the end, go ahead and enter them there, and we will address them as we go or when we get to the end. So many of you already probably familiar who we are. Diagnomatic. We are a manufacturer of diagnostic imaging phantoms. We also make a software platform that analyzes the images for you and automates the QA process. May know us under our former name, Pro Project. I say former, we still operate under Pro Project, known mostly in Poland, kind of Diagnomatic elsewhere. So let's jump into purpose of phantoms. Phantoms are basically tools that mimic human body and tissue, and we want something that we can have a repeatable image to verify that best possible images. I mean, they're specialized tools that we use to simulate human tissue and organs and serve several critical purposes. They provide a consistent standard for calibrating and testing diagnostic imaging systems. They ensure that our machines produce accurate and reliable images. Phantoms are also used for assessing and adjusting the performance of imaging devices, such as their resolution, contrast capabilities. When changes are made to an imaging system or when comparing multiple systems, phantoms help verify the quality of the images that remain high and consistent, and, which is essential for accurate diagnosis and ultimately patient care. So some of the typical parameters we're going to find are spatial resolution, which is the ability of a system to distinguish between objects or features in an image. Contrast resolution, which measures different levels of brightness. Dynamic range, which is the ability of a system to capture subtle details and such as soft tissue or high contrast areas such as bone. Homogeneity, which refers to the consistency of the appearance of tissue in imaging standards. So when we're looking at various standards and guidelines for phantoms, they can vary. Can be driven by county or state regulations, and these standards can vary in ways. In some cases, hospitals and medical physicists have to establish their own routines for testing. I think most important is to have a repeatable and reliable constancy tests. Constancy tests are procedures used to check the output of a diagnostic imaging system and make sure that it remains constant over time. Consistent image quality is crucial for the accurate diagnosis and monitoring of medical conditions. And this emphasis on quality assurance in medical imaging is critical for patient safety and the effectiveness of medical diagnostics. Without consistent standards and guidelines, it can be difficult to maintain a high level of image quality required for accurate diagnosis. So you can see here we have top level. You might have legislation requirements. You have in Poland, probably in the U.S., most popular, the most well-known is the Mammography Quality Standards Act, overseen by the FDA. But after that, you primarily have various recommendations. So as you notice, as you look through probably any of our Phantoms or any other manufacturer Phantoms, it's going to address a lot of these various standards, word soup, if you will. So it's always important to know what standards are required, whether at your facility or which country you're in, or even what state you're in if you're in the States. All right, so let's jump into some of the actual Phantoms themselves. Some of the more basic ones are test patterns, step wedges, geometry cone, copper and PMMA filters. And kind of the back half are some of the Phantoms that we manufacture that kind of combine a lot of those basic Phantoms. Some you're probably already familiar with. And we'll walk through those and do a little comparison as well with that Pro-Digi and Flua, because we get a lot of questions regarding which is going to be the better option for end users. So let's start with test patterns. These are typically made out of lead and are made up of various line pairs. And what it's doing is referring to the pairs of alternating dark and light lines that are used to test the ability of the imaging system. The higher the line pair frequencies indicates a better resolution, meaning a system can distinguish smaller details. So there's a lot of different variety of these, different shapes, different line pairs, referred to as different bar types. Again, it's important to know which is going to be best for the system you're working on or the regulations you're working with, which bar type is going to best suit the equipment you're using. Our second type of Phantom, looking at step wedges. Again, pretty simple piece of usually aluminum. Can make them in various types of aluminum. Sometimes different parts of the world require due to local testing. But these are used to optimize exposure settings and can help assess how a system responds to different thickness and densities of materials. So whether it's different tissues, bone, etc. And then they'll help monitor changes image quality over time. So this is a typical one as well. Geometry cone. This guy's made out of copper. It's used primarily for aligning the X-ray tube and the imaging receptor. Can be useful for analog or film cassette as well as a digital detector, and helps ensure the accuracy of and consistent imaging. Also helps ensure the X-ray beam centered and aligned perpendicular to the imaging receptor. And collimation ensures that only the necessary areas exposed to radiation. So it reduces unnecessary radiation exposure to the patient and helps improve your overall image quality. So here we have a pair of different filters, first being copper filters. Copper filters have a relatively high atomic number, which means that it effectively attenuates X-rays. These automated exposure control systems rely on detecting the amount of radiation that passes through the patient to adjacent exposure parameters. And these copper filters provide a known measurable level of attenuation, which allows technicians to verify that the AEC system is correctly responding to changes in X-ray intensity. PMMA filters, or polymethyl methachlorate filters provide a standardized thickness and composition and ensuring consistency of these test conditions. These have a similar density to human tissue, and when placed in X-ray beam, these filters mimic the absorption and scattering of X-rays that occur in actual human tissue. So it provides a realistic test scenario for these AAC systems. So now that's what brings us to our first kind of combination, and you can see where we have all these previous phantoms all come together in a single phantom. So the Prodigy is made of PMMA, sits on a copper plate, and then it has all these various aspects to it. So there's that geometry cone in the center for perpendicularity. Got a copper wedge on one end. There's a test pattern or a line pair resolution built in, low contrast element with a aluminum step wedge. You've got a little free area for signal calibration, as well as the markings on here to help determine the size and position of an effective radiation field. So kind of basic setup. A couple photos here. One of our very own Merrick setting up standard X-ray machine. But there's some various accessories for hanging the phantom. If you're doing chest X-ray, like seen on the right. Some tests need to be performed with with something resembling a body patient between the tube and the detector. And some of these X-ray devices will have a slot right underneath the tube. For others, we can use the Pro-F stand and set that up above the phantom. Photo of the C-arm apparently has disappeared, but you would also use the stand for C-arm, which are in various operating rooms, and angiographs used for cardiology and vascular surgery. So once we have the phantom set up, we can grab an image, and here's just kind of a breakdown of some of the different tests that we're looking at. So first being the central beam perpendicularity. So what we're looking at here is a little white dot in the imaging center, which fits within the inner circle, perpendicular. So if it fits within there, the perpendicularity is off by less than 1.5 degrees. And the effect is achieved thanks to the ball placed at the top of the cone and the ring at its base. The cone itself can be a little delicate, so when handling, best to maybe remove between testing so it does not break off. Second, dynamic range. This is evaluated. This is with the built-in copper step wedge. In this case, it has 7 steps, different thicknesses. And here, the number of steps should not be smaller than 1 from the reference value. That's according to DIN 6868-4. It should be noted that the exposure, it's recommended high voltage of 75 kilovolts. Should always do your testing on clinical settings. Sometimes the panel will have a recommendation, but again, for general rule of thumb, do your testings with your phantoms on clinical settings. Next is our spatial resolution. This is where we're using the zoom tool. We assess the high contrast spatial resolution pattern, the relevant part of the image, which is in that area 3 there. Respective line pairs are in millimeter values, line pair per millimeter, and specified for each bar pattern. And here the number of line pattern groups should again not be smaller than 1 from the reference value. Again, recommend using that 75 kilovolts, and for constancy tests, we want to make sure we're always using the same kV value for each one of these tests. Regarding the low contrast resolution, this is determining the number of visible low contrast objects. So similar to the copper wedge. We move to homogeneity. Here we're going to check for any artifacts, see if they're visible in the central area of the phantom, central number 5 region. And this is part of the image does not contain any test objects, so you can also use that area for a signal to noise ratio measurement. And ideally, you want to have that phantom image should be homogeneous and free from any artifacts. And lastly, we have the collimation or beam alignment. And this is measuring the distance between the light fields, here represented by correspondent markings visible in the phantom's image, and the X-ray edges in the direction of perpendicular and parallel to the anode-cathode axis. One can see the scale visible in the actual phantom image. And then we have formula to help calculate that. I'll show that here in a moment. So here's a breakdown of the tests again. This is kind of looking as if you were testing via the software, and shows how the different tests would pass. Their test pass when the beam is perpendicular. The sum of the differences between the light of the X-ray field, the horizontal and vertical direction, and should not be greater than 3%. The FTD and the sum of the differences should be greater than 4%. Looking at the high contrast resolution test, this test is passed when the spatial resolution does not differ more than plus or minus 1 with a group line pair from the baseline value. The low contrast resolution test, this test is passed when the number of visual low contrast objects are greater than 3. Here we have our dynamic range test, where we want to have a visible 7 different grayscale steps. And then ultimately our homogeneity test. We want all our images to be free of artifacts. And here's a little formula that's used to help test the non-uniformity factor. And we want that number to be greater than 12%. Some of these standards may change depending on, again, standards or regulations. So this is kind of the baseline that we have built in, but just gives you a kind of example of how what those can look. So now let's briefly look at the ProFlua, the 150. This is designed a little differently. The ProDigi is designed for 2 different standards, the DIN, the 68684, and then the 6868 150, which kind of gives away the name, like ProFlua 150. This is designed, we're not going to get too much into the fluoroscopy, but this was designed for both analog and digital radiography and fluoroscopy. So if you're in a facility that has both and you kind of need an all-in-one tool, this can be helpful there. So design's a little bit different. There's some similarities to the ProDigi. We'll walk through those differences here in a moment. Setup with this is going to be very similar to the ProDigi. You have some various tools to hang up, whether setting up C-arm or hanging for chest X-rays, etc., including various filters. So if we're looking at the testing, all the test elements are placed in a central circle, which is helpful for testing older fluoroscopes and using circular detectors. So the Phantom consists of both grids and circles. You might also notice too, there's a lot more copper steps, 17 here. The spatial resolution that the line pair is actually the exact same as the Pro Digi. Contrast resolution, we've got 8 steps instead of 6. Contrast resolution, then 17 instead of 7. We still have that, collimator light field and beam alignment area, so that's very similar. And same with the beam perpendicularity, that the cone there is the same, and still gives you that central area for determining if there's artifacts. So kind of broken down just in a real simple. Really, one's designed more for straight up radiology, the second for radiology or fluoroscopy. Again, 2 different standards here. And there's just a few kind of physical differences as well. 150 is a little thicker, both the PMMA and the copper plate, and then obviously have more step wedges, or the copper wedges, and the low contrast elements, and they're different values as well. So again, because they're built for 2 different standards, so could be helpful to you or an end user. So ProStand allows us to do some different testing. Works with our ProSlit camera. Also works with our pinholes, and then it can also help you with your HVL measurements. There's kind of a basic version and full version, if you will, that has a 10-degree tilt, which tends to be used more in mammography. So first, we're gonna look at the ProSlit camera, which is a way to primarily focus the focal spot size. And there's some various steps here, but it's a relatively simple tool. More of the calculations on the back end can maybe a little more difficult, but I'll walk you through what we're doing setup wise. But primarily what we have this is, since we know the width of the slit, we can the enlargement factor, and we can measure the slit image width, and then calculate the focal size from that. So we're actually making 2 different exposures here with the slit 90 degrees apart. We'll look at what that looks like here in a moment. Again, setup wise, we want that effective focal spot. The slit sits at the reference point. We have the reference axis, and then where the plate receiver sits on the bottom. And again, we want the tool to sit in parallel with the anode-cathode axis, focal spot, be oriented perpendicular. Once we get some numbers, we can adjust the slit and the receptor distance, so we can obtain the enlargement factor we're looking for. And that's created by using the little formula here. That's an M underneath the logo and the image. And ultimately, we're measuring the distance between the selected marker, calculate the enlargement factor, and here's where the actual distance between the markers here. There's that image itself of how it'll look up there with the anode cathode, the focal spot length, focal spot width, and then we can determine that size using that formula, and then see where it fits within the compare the result to a reference value, which is in the included table. To also simplify it by our software can actually calculate this for you, so that can help speed up that process for the technician or physicist. And the last one we're going to look at here is the X-ray, the pinhole assembly. And this is just a way to get quick and easy measurements on the focal spot size. This typically is not used for routine checks. It's used more for diagnosis of X-ray machines if you're getting bad quality. Again, this is something else that applies to fixes to the ProStand, and then based on the geometry, the stand pinhole positioned related to the focal spot in the detector. And once the exposure for measuring the width, the length, the X-ray factor, then we divide by the enlargement factor, and then we compare these measurement values with the maximum limits stated in in the standard. And here's breakdown of chart on the right there, the different focal spot values. Just briefly on the software, a lot of you are probably familiar with it already, but the software is designed to automate the QA process. We have it designed to work with a lot of different phantoms we made, but here's just a quick process. Once we get an image DICOM of the phantom itself, we have a couple ways that we can either push an image to the cloud, or we can use the diagnomatic connector, which automatically will send those images to the cloud. And that's where everything gets analyzed. It's all pushed images, and once an image is analyzed, typically about 5 minutes, you get a quick notification, an email, and lets you know the status of your equipment. And a lot of the radiology phantoms that we were looking at here earlier do work with the software, so our ProDigi or ProFlua, the copper plates for AC testing, Pro contrast. We didn't mention much in mammography, but a handful of the mammography phantoms work on here as well. It's a similar process, and then the Pro slit is another one that works with the software. And then ultimately you'll get an image. It's going to break down all those different tests for you, give you a breakdown, and show you images, and allows you to run tests and or rather run reports. And again, it's all about help simplifying that QA process. And just briefly on the connector. The connector is something that gets installed once. It just runs in the background. Once it's installed in a system, any of the imaging devices in the center can have their images sent to the cloud, and you choose the relevant phantom images, and those are all encrypted, analyzed, and sent back to you. So that's kind of what we were covering for today. It was relatively quick and painless. Have Tomas on the line here as well. His audio seems to be a little wonky at the moment, but if anyone has any questions, or for myself or for Tomas, we're available for you here. Or if you have come up with questions later, you're welcome to email me at tom.douglas@diagnomatic.com. And this might be a quick and easy one. All right. Well, again, we do have a recording of this, and this will actually be popping up. If you weren't following on LinkedIn, I believe this videos will be on our Diagnomatic page on LinkedIn as well, so you can view again, sent elsewhere. All right. Doesn't sound like we have any questions, but oh, maybe we have one. Hang on here a second. Or maybe not. All right. Well, thanks so much. But yeah, if you have any questions, Yeah, well, there's one unrelated, but yeah, with regard to the MRI, yeah, you can email me about that too, Cheryl. So yes. All right. Well, again, thanks everybody for joining. We're gonna sign off, and until next time, have a great day.